Good morning, this is Vern Nelson. I hope you're all doing well. This is Semiconductor Devices for March 17th. I haven't had a chance to talk to you guys yet. I've been pretty busy. I'm trying to throw together some lectures so that you guys can watch them and then hopefully do some problem sets. So this lecture is a carry-on from last week's lecture. So last week we started how to analyze transistor amplifiers. And this was from an AC analysis standpoint. And I think I introduced it last week and I said that there's a lot of things you have to take into consideration when you're analyzing transistor amplifiers, and there's a whole bunch of different concepts that you have to kind of master, and then you have to put them together in order to do the analysis. Some of them we talked about last week. We talked about the two-port model with an input and output port, which is a dependent voltage source looking something like this. We talked about characteristics of the input port, what makes a good Z in, Z out, and we did a couple of examples of how to run through the two-port model to figure out what the input currents and voltages are, what the outputs are, and then how to figure out the current gains, voltage gains, etc. We talked a little bit about other two-port models. That there's that the one we're dealing with is it's an approximation of the full model, which has bidirectional action and kind of hard to solve unless you use simultaneous linear equations. And then there's a whole bunch of Z parameter, Y parameter models that make it even more difficult. But we're going to try and keep it fairly straightforward. These more advanced models, basically the simple model gets you probably like 5 or 10% error, and then the more advanced models, now you're working down from 5% down to probably 1%. So doing a whole bunch more work for not a huge improvement isn't really worth it, and we're going to do the basic models. Okay, so I think got to this point. I said there's this thing called the H parameter. And the H parameter model, it's the one that we use when you analyze a transistor, and it's the full-blown model that they use for the transistor, where they model it as a dependent current source, which has some multiple here called HFE. We've been calling this beta, but in the H parameter model it's called HFE, and basically this current here is HFE times IN, so this current is a multiple of what's coming in this way. So you inject a current here and you get HFE times bigger current flowing this way. This little voltage source here on the input, there's a little bit of a voltage source on the input side, and what that is if you come along, if you put a voltage on here, if you apply a voltage to the output, some of it may leak back through the transistor and appear in the output. So this is to model reverse leakage current in the transistor, which is a small effect and we usually ignore it. HOE here, this is called output admittance. And what it does is if I put a voltage here again, the current going into the output will actually go up a little bit if I change the voltage. So it's not a perfect current source, and we model that effect by putting a parallel resistance in with the current source to model that leakage. Now this is an admittance. Be careful because this is actually an admittance. So this is in microsiemens. It's 1 over ohms. So this is the full-blown model, but this HRE makes it really difficult to figure out what the actual currents are, and it makes a small effect. So we usually throw that away and we come up with what's called a simplified H parameter model. You can see that the voltage source on the input is gone. That's the first simplification. The second simplification would be to take away HOE. Again, it has a small impact. It's there. but for most circuits and kind of figuring out whether or not it's biased and what the gain is, it doesn't really make that big a difference. So we often throw that away too. So this is the H parameter model, and you can simplify it even further. Now a variation on that is something called the T model, or the T parameter model. And the T parameter model is a little different. Basically, we have a current source. This is a dependent current source. The current comes in here, and it gets amplified by this current source and results in a larger current flowing from collector to emitter. So that's pretty much the same. What is different, though, is that this value of R prime E is about beta times smaller than this HIE. So HIE up here and R prime E, both of these things are trying to model the same thing. They're trying to model the impedance of the base emitter diode, but they do it looking as though those impedances are at a different point. And in order to understand that, we have to talk about something called reflected impedance. So reflected impedance is it's an impedance in a circuit at one point. We're going really low tech here today. I'm hoping it's going to get better, but for today this is what you got. So a reflected impedance is an impedance at one point in a circuit that may look different when it's viewed from another point in the circuit. So for example, here I have this 12 ohm resistor. If I basically say, what is the impedance looking that way at the 12 ohms? The answer is it would be 12 ohms. However, if I come back here to this source, if I've got some stuff in between here that separates the 12 ohm resistor from the source, as far as the source is concerned, it may not look like 12 ohms. It may look like even 1200 ohms. So a reflected impedance is one that, hey, if I stand here and look at it, it looks like 12 ohms, but if I come back here to this side of the circuit, it looks like 1200 ohms. And one of the places that reflected impedance is often used is in transformers. High tech here. Look at that. So here's an example of a transformer. Basically got 120 volts RMS coming on this side out of a wall plug. So that source is connected to a transformer with a 10-to-1 turns ratio, so it's reduced. 120 volts RMS on this side ends up being 12 volts RMS on the other side. So 12 volts on this side. How much current is that? So the current going into the 12 ohm would be 12 volts over 12 ohms, which would be 1 amp RMS. So at this point, it's a 12 ohm resistor. It's got 12 volts across it and 1 amp through it. However, when I come across to this side of the transformer, so looking this way, from this side of the transformer looking that way, the impedance looks like 12 ohms. However, if I come back to this side and I say, well, what's the impedance looking at that 12 ohms from over here? Then what I have to do is I have to figure out the voltages and the currents that's seen looking that way. So we already said it's 120 volts at this point. Now the thing about the transformer, that if you have a 10-to-1 turns ratio, over here it's 120 volts, and on the other side it's 12 volts. So the voltage goes down 10 times. If the voltage goes down 10 times, then the current goes up 10 times. So over here I have 1 amp. Way back over here I will have 0.1 amps. And I can rationalize that because basically the power, a transformer is very efficient and it doesn't have much power loss. So the power that's being put into the circuit has to be what appears in the 12 ohm resistor. So at this point here, if I said this power, I'd say it's IV equals 0.1 times 120. That's equal to 12 watts. So 120 volts and 0.1 amps over here, 12 watts going into the transformer, gets coupled over to the other side. Power on the other side equals IV equals 1 amp times 12 volts equals 12 watts. So you can see we've conserved power. Power going into the circuit is what gets delivered to the resistor. But what is the impedance that the 120 volt source thinks it has connected to it? To figure out the impedance looking from this point, I would take, so that's the Z, I would take Z equals V over I, which would be 120 volts over 0.1 amps. That's equal to 1200 ohms. So as far as this guy is concerned, this voltage source, he does not have 12 ohms attached to him. He has 1200 ohms attached to him. So the 12 ohm resistor, when we look at it from this point on the circuit looking that way, we can see it as a 12 ohm resistor, but when it's reflected across the transformer, it gets converted into a 1200 ohm resistor, so it's being seen as a different resistance when it's looked at from a different point in the circuit.